So today we are going to start with 4-bit ring counter. Okay, so this is what is your 4-bit ring counter is, and as you can see for its connections, how are the connections? You can observe over here. This 4-bit ring counter consists of 4 D flip-flops. D flip-flop A, B, C, and D. Okay, so each D flip-flop is having 2 inputs, D input and clock, and one output is shown here Q, but Q bar is present here. Okay, and one more asynchronous input is shown here, which is called as clear, and this clear signal or clear pin or clear input is asynchronous type of input because it will not need clock pulse for its operation. So once you activate it, clear signal, once you activate the clear signal, all the outputs of flip-flop will be resetted. That is, they will be equal to 0, 0, 0, 0. So for that purpose, this clear type of asynchronous input is used in flip-flop. Now, as you can observe here, the clock signals of each flip-flop, they are connected together and tied to a single terminal where a common clock source is applied here. And as you can see, uh, the output of flip-flop A is connected as input to flip-flop B. Output of flip-flop B is connected as input to flip-flop C. Output of flip-flop C is connected as input to flip-flop D. And what you can observe here is output of flip-flop D is connected back as input to flip-flop A. Okay, so this is what is the connection of your ring counter. Okay, so there is a feedback between last flip-flop and the first flip-flop. Now here you can observe the output is taken as QA, QB, QC, QD. So 4-bit data is taken out parallelly here. Okay, so that is what you can observe about the 4-bit ring counter. So here, what is speciality of this ring counter is that it is just like serial in, serial out type of shift register, but here the feedback loop is provided. This additional thing is present, okay, in, serial out shift register. So if you add this feedback to serial in, serial out shift register, then that shift register is converted into a ring counter. Okay, now let us see how this ring counter works. Okay, so let us see the working of this type of ring counter. So initially what is done, all flip-flops in the ring counter are resetted to 0. And how this is done? This is done by applying clear signal to all the flip-flops. Okay. Now, before applying clock pulse, what we have to do is we have to apply logic 1 to the ring counter, okay, for each clock signal. And what will happen? The data will circulate among all the 4 flip-flop stages of the ring counter. Okay, so this 4-stage ring counter is called as mod 4 ring counter or 4-bit ring counter. Okay, to circulate the data correctly in the ring counter, we must load the counter with required values like zeros or all ones. Okay, so that is what should be done. Now, if you see the truth table of this ring counter here, what we are doing initially, we are applying clear input to the all the flip flops, so that the output of all flip flop equal to 0. Then what we do, we set the flip flop to 1. Okay, and then we deactivate the clear signal. So we are going to make clear equal to 1. Okay, now the ring counter will start with its operation. Okay, what will happen here is for first clock signal, the counter will start its operation, and on the next clock signal, the counter again resets to 00, and ring counter has 4 sequences: 0001, 0010, 0100, 1000, and again back. Okay, so these things are done here. I will show you how this happens. So as you can see, initially all the outputs, if we apply a clear signal here, then all the outputs of flip-flop will be 0. So once you reset this, then what you are going to do is you are going to apply logic 1 to this D input, and then apply a clock pulse, and at this time deactivate this clear. So remember to deactivate this, otherwise output will always be 0. Now once you apply one clock pulse here, what will be the output of the flip flop? It will be 1, 0, 0 and 0. So this is your second output. Now what you do is apply 0 here and then apply the next clock pulse. Now if you do this, what will happen? This 0 will be shifted into the flip-flop 1. Okay, so let us use some another color. So 0 will be here. Okay, now this 1 will be shifted to next flip-flop. So next flip-flop is having output equal to 1. Now this 0 will be shifted to next flip-flop. So there will be 0 here. Again here there is 0 which is shifted to next flip-flop. So again 0 will be there. Okay. Now you can observe here 0, 1, 0, 0. Okay. For second clock pulse. Now suppose if we apply the third clock pulse, then what will happen? So if we apply the third clock pulse, then you can see that this 0 is circulated back to input. So output of flip-flop A will be 0, output of flip-flop B will also be 0. Now this 1 will be shifted to C. It will be shifted to C, and 0 will be shifted to D. So now the output will be 0, 0, 1, 0. Again apply next clock pulse. So if you are applying next clock pulse, then this one will be shifted. Where it will be shifted? It will be shifted to D flip flop, and this 0 will be shifted back to first flip flop. So there will be 0 at the output of first flip flop, 0 at the output of second flip flop, 0 at the output of third flip flop, and 1 will be there at the output of fourth flip flop. Okay, so after application of the third clock pulse, you will observe the output of ring counter to be equal to 0, 0, 0, 1. Now once again, if you apply a clock pulse to this ring counter, then again you will observe the previous state will be repeated, because this 1 will be given back to your first flip flop. So your first flip flop is now having 1 as output, or flip-flop A is 1, flip-flop B is 0, flip-flop C is 0, and flip-flop B is 0. So again you are getting the first state, and the same thing will be repeated each time you are going to apply the clock pulse. So you will require 4 clock pulses to come back to the previous state. So it keep on circulating the data within it. So this type of counter is called as a ring counter. Are you clear about this, or do you have any doubt in this? If you have doubt, you can ask me. So how operation is carried out? Initially clear signal is applied, which makes output of all flip-flops equal to 0, and thereafter this clear signal is deactivated, and then this D input is made 1 and the first clock pulse is applied, and when the first clock pulse is applied, 1 will be outputted at flip-flop A, 0 will be outputted at flip-flop B, C and D. So 1 is there in A position. Now what happens is here this preset is deactivated, and thereafter if you apply a clock pulse, this every bit will be shifted towards right. So this will be shifted here, and this 0 is going to shift in the first position. So the next output will be 0 1 0 0. The next output will be 0 0 1 0, and next output will be 0 0 0 1, and after this we'll be getting output again as 1 0 0 0. Okay, so this is how this type of counter works. Okay, so this is all about its working. So I'm going to provide you notes, and for that what you have to do is you have to enroll yourself for Moodle. I'm going to add your second semester subjects there. You have to enroll to second semester subjects, and on the second semester subjects, I'm going to provide you all the study material. Okay, and also assignments for second semester. So you have to write 2 assignments, one for each paper. For E1, 1 assignment of 5 marks, for E2, 1 assignment of 5 marks, and we'll be conducting internal examination for E1 and also for E2, and both are for 10 marks. Okay, so for theory overall there are 15 internal marks, and they will be calculated like this. And for practical, there will be again 35 plus 15, and as I have already discussed with you, these 15 marks will be related to survey, market survey. Okay, online market survey for a certain electronic product. Okay, so that is what you'll be doing, and you are submitting it. We'll talk in detail about this during your practicals. Okay, I think you have performed first 3 practicals, and on this Saturday we are going to perform remaining 3 practicals. 3 plus 3, 6 practicals in all you are going to perform during your examination, and you are going to submit the sheets of all these 6 practicals. Okay, so this is very important as far as your all activities are concerned, and all these activities have to be uploaded on your Moodle. Okay, so let me once again share with you. No, not this. So we were discussing about the ring counter, isn't it? So working principle we have seen. We have seen the truth table. Now let us draw a timing diagram from this truth table. It is very easy to draw it. Okay, so first you have to draw a clock pulses, and then you have to give the output of Q0, then you have to give output of Q1 according to your truth table. Okay, so here you may observe 1 0 0 0 0 1 0 0. So I'll write it here. So this is 0 1 0 0. The next step will be 0 0 1 0. The next step will be next step is here 0 0 0 and 1, and thereafter again you have 1 0 0 0. Okay, so it is like this. So like this, you have to draw the timing diagram. I'll be giving this diagram to you in your notes, so don't worry about it. So it is very simple to draw by looking at the truth table. Now let us discuss what are the advantages and disadvantages of ring counter. So as far as you consider this 4-bit ring counter, you can see it can be implemented using D flip-flop as well as it can be implemented by using JK flip-flop. So both flip-flops can be used to implement it, and it is self decoding circuit. It don't need external extra circuitry for decoding. And its disadvantage is that only if you consider 4-bit counter, then as it is having 4 bits, 2 to the power of 4 equal to 16 states. All these 16 states are available, but these 16 states are not utilized. Out of these 16 states, only 4 states are utilized. Only 4 states are utilized. This is what is a disadvantage of the ring counter. Okay, so generally this type of ring counter is used in rolling displays. You might have observed the or you might have seen the rolling displays in your day-to-day life. So to roll a particular thing continuously, this type of ring counter is used. Okay, so this is all about your ring counter. Now let us see the next part of this, and that is what you can see on the screen. Can anybody tell me what you can see on the screen? Read it out loudly. Read it out loudly, what you can see. Yes, students. Atharva, Mayur, Sai, Sakshi, Tejas. Can you read something on the screen?
Modulus counter.
आवाज येत नाही तुमचा मला आज. काय माहिती, आज तर मी वायर्ड हेडफोन्स वापरले तरी पण आवाज येत नाहीये. काय गडबड आहे काही कळत नाही. पण SY चा आवाज मला व्यवस्थित ऐकू येतो आणि तुमचा का येत नाहीये ते कळत नाही मला. आणखी कोणतरी बोला बरं. साई बोलतो का? साई बोल बरं.
मॉड्युलस काउंटर.
तुझा आवाज येतच नाही मला. काय माहिती तुमच्याच क्लासला असं का होतं. बरं ठीक आहे. आता the last point of this chapter we'll be discussing now, which is called as modulus of counter. Okay, modulus of counter indicates the number of states that it can count. Okay, so mod n counter can count n number of steps. Mod n counter can count n number of steps. Okay, so this is very simple, what you can say, concept. Modulus of counter is a simple concept. Suppose if you have 2-bit counter with you, and if you want to count modulus of this counter, then this modulus of counter will be equal to 2 raised to number of bits, that is 2, which is equal to 4. So this is called as mod 4 counter. What it is called as? Mod 4 counter. Okay, so you write it down. This is very important for examination. Now if you consider 3-bit counter, then what you can say is how you are going to count modulus for it. Mod equal to 2 raised to 3. So 2 raised to 3 is 8. It can count 8 states, and therefore this is called as mod 8 counter. Okay, similarly 4-bit counter can be called as mod 16 counter because it is capable of counting 16 states. Now the question is whether all these counters, they are going to count in a multiple of 2. This is not so. Even you can have mod 3 counter, Mod 5 counter, Mod 7 counter, Mod 6 counter, etc. But you will require some external additional extra logic for it. So mod 3 counter means it is capable of counting 3 states. Mod 5 counter means it is capable of counting 5 states. Mod 7 means it is capable of counting 7 states, etc. Okay, so this is all about the modulus of the counter. Now, you should know what are the applications of the counter. So, counters are basically, they can be used for frequency generation because they work as divide by 2, divide by 4, divide by 8 frequency counters. Okay. So, if one frequency is applied to it, it will produce half of it, one fourth of it, one eighth of it, like that. So in this way, frequency counter, it can be used as a frequency counter. It can be used as digital clock. Okay, it is used for time measurement. It is also used in analog to digital converter. As I told you, it is used in frequency divider circuit. Okay, it can be used to generate the triangular waves. So these are some of the applications of the counter. And as far as your shift register is concerned, shift register can be used to store the data, and they can be used to shift the data, they can be used to rotate the data. And all these operations can be carried out in CPU. So in central processing unit, set of registers is present, and set of registers is used to store the data temporarily within its internal memory and to carry out operations over that data. So it is used as a scratch pad for your microprocessor or central processing unit. So that is what is application of your shift register. So in this way, your counter and shift register chapter is completed over here. And after this, we'll be going to the third chapter of computer organization afterwards. Before that, we are going to discuss about the third chapter of your paper number 1. Okay, so that we'll be doing. So let me share with you. I will stop sharing this, and so the third unit of your paper number 1 is smart instrumentation system and smart sensors. So in this, we are going to learn about block diagram of smart instrumentation system, concept of smart sensor, film sensor, and nano sensor. So these concepts will be covering in chapter number 3. Okay. So I think we have already discussed about the smart sensor during our previous lectures. So today I'm going to revise about this. As you can see here, this particular picture shows a smart sensor, and this is a sensor which takes input from physical environment and uses built-in computing resources to perform some predefined functions upon this detected signal by the sensor. Okay, and after processing, it will provide data to the user. This is what is the definition of the smart sensor. Now, if you observe the working principle of the smart sensor, you can observe its block diagram over the screen here. So there are three important parts of this smart sensor. One is the sensing element, which is basically your sensor, which converts some physical or chemical stimulus into equivalent electrical signal. And next, the signal processing is carried out, signal conditioning is carried out, and thereafter interface is present in this block, which is called as the sensor interface. So sensing element, signal processor, and sensor interface, these are the three parts of your smart sensor. Now, if you observe here, you can observe three important blocks are available in your interface. Uh, so whole of this is called as a processor of the sensor, and this processor of the sensor, it consists of multiplexer, and it requires a current source. Multiplexer requires a current source. It operates on a current source, and through this current source it is activated, and output of this multiplexer is provided to analog to digital converter, and after converting it into digital form, it will be applied to what is known as digital signal processor, and then the output is provided to the user. Okay, now as you can observe here, there is facility for multiple inputs. So if multiple input facility is there, the smart sensor is capable of detecting or measuring multiple physical or chemical parameters. And for this reason, you will require multiple sensors. Suppose if you want to detect 4 parameters, you will require 4 sensors. If you want to detect n number of parameters, then you will require n number of sensors. Okay, so output of each sensor is to be provided based on your uh, time division multiplexing concept. So a certain time slot is provided for each sensor, and during that time slot, a particular sensor will provide its output to the user, and continuously the slot will be provided to all these sensors, and this frame is repeated continuously. So some slot is given to 1, some slot is given to 2, some part of slot is given to 3, some part of slot is given to 4. So a whole time period is divided into 4 slots in this particular example, and each sensor will get its round during this whole time period, and this frame is repeated continuously. Means after 4 rounds are over, again sensor 1 will get its own round, like that. So this multiplexer is used for this purpose. So what multiplexer does, it takes or accepts the inputs from multiple sensors, and at a time it is going to connect one sensor at the output, and to which sensor is to be connected to output, it depends on the algorithm which is stored within the processor of this smart sensor. Okay, so this division particularly may be based on timing. Suppose if you have overall, I can say 4-second timing, then this 4-second time is divided into 4 slots of 1 second each, and 1 second each is provided for each sensor. So initially sensor 1 will be connected to all this system and provides output within 1 second to the user. During next 1 second slot, sensor 2 will be connected. During next 1 second slot, sensor 3 will be connected. And during next 1 second slot, sensor 4 will be connected. And this will be done continuously. Okay, so all sensors are scanned continuously. So function of the multiplexer is to uh, provide this facility, multiplexing facility, that is one out of many to be connected based on some predefined algorithm to the internal components of the smart sensor. Okay, now here you can observe the analog to digital converter block. As you know, output of sensor is in analog form. It has to be converted into equivalent digital form. Because we are using digital signal processor to process the signal which we are getting from the sensor. Okay, so therefore, this analog to digital converter is used in order to convert analog signal available from sensor into its equivalent digital signal. And this digital signal is applied to digital signal processor. And there, the signal conditioning is carried out and number of mathematical operations are performed on the signal which is provided by the sensor. And when it comes into its desired form, it will be made available to the user. Okay, so that is what is the basic working principle of your smart sensor. That is what you can see here. Okay, so here you can observe which kind of technology is used here. Microprocessors are used to process this data. So uh, very large scale integration technology is used to integrate these number of components into the processor. At the same time, MEMS are used, uh, micro electromechanical switches. They are used for making sensors here. So these two technologies are used. Now, what are the applications of smart sensor? Applications of smart sensor. First application is communication. They are used to exchange the information. If the sensors are used to exchange the information, then they are communication type of smart sensors. They are also going to provide multi-sensing capability. For example, if some industrial process is there, and for that process you are going to control the physical parameters and chemical parameters of that process, and in that case multiple sensors have to be used to control all these things automatically and to provide the controlled environment for that particular industrial process. So multi-sensing is this application of the smart sensor. Then they are also used for computation. Okay, so if certain measurements have to be done of certain environment and that is provided to the user for computation, then for this purpose also the smart sensor is used. It can also be used for self calibration and provide the measurement of any parameter, any physical parameter or any chemical parameter. Okay, now as you can see, the smart sensors, they are using wire technology to transmit their data, but nowadays wireless technology is also used to transmit the data of the sensor at remote places. Okay, so such type of sensors are called as wireless sensors. Okay, and such a large network of sensors can be formed to collect the data from various locations. Okay, so this field of sensors is called as wireless sensors and wireless sensor networks. So this is gaining importance nowadays. Okay, so now we are going to the next point of your syllabus, and that is thin film sensor, as you can see in the diagram. Okay, so these type of sensors are produced by directly depositing material. Okay, and generally the vacuum deposition technique is used for this, and it is called as a sputtering. So this process is used to form thin films. Okay, and they provide high degree of repeatability of their production. So such type of sensors are called as thin film sensors. Okay. Now, uh, as you can see here, the different type of techniques which are used for thin film sensor manufacturing. Uh, these different technique, name of these techniques you need to know. Chemical vapor deposition technique, physical vapor deposition technique, and molecular beam epitaxy, atomic layer deposition technique. So these are some of the names of the techniques which are used to produce the thin film. Okay, and uh, the width, thickness of this film range in the range of nanometer. Okay, so only these two things you have to remember about thin film sensors here. Okay, now thin films can be created from a wide range of materials. Okay, these materials may be polymers, nanomaterials, oxide complexes, thermoelectric materials, silicon based materials. So you remember these materials also: polymers, nanomaterials, oxide complexes, and thermoelectric materials, and silicon based materials. They are used to form